There is a moment older than time itself, a moment when everything you have ever known, every star, every world, every breath, was still waiting to exist. Before galaxies spun themselves into spirals, before atoms learned to cling together, before even darkness had a name, there was only a silent, infinite potential. And then something changed. Not with an explosion as we imagine it, not with fire or thunder, but with a quiet, immeasurable unfolding, a release of pure creation so vast, so gentle, so perfectly balanced that it shaped the blueprint of reality itself. Physicists call it the Big Bang, but in truth, it was less like a bang and more like the first heartbeat of the cosmos, an expansion from nothing into everything, from stillness into time, from emptiness into light. As you settle into this journey, allow your mind to soften, because tonight you will drift back to the very beginning to witness how the universe opened its eyes for the first time, and how, in that opening, the seeds of stars, planets, oceans, and life were quietly, delicately set into motion. In the beginning, there was no time, no ticking rhythm, no unfolding sequence, no before or after to hold anything in place. What existed was a silent field of pure potential, a state so absolute and so undisturbed that the word nothingness fails to describe it. There was no darkness, because darkness requires space. There was no emptiness, because emptiness requires structure. There was simply a stillness so complete that it lay beyond imagination, something you cannot picture, only sense as a faint, almost distant idea, lingering at the edge of awareness. And then, in this infinite quiet, something shifted. Not a sound, not a burst, not an explosion as we often imagine, but a gentle transition like the soft, slow inhale of a sleeping universe preparing to wake. Physicists describe this origin as a singularity, a point of infinite density and infinite temperature, where everything the cosmos would one day become was compressed into a space smaller than a grain of dust. But this definition, while mathematically perfect, misses the deeper truth of what it felt like, because the singularity was not just dense, it was full of promise, containing every star, every galaxy, every atom that would one day dance across the universe. Every particle that forms your body today was once curled inside that first, impossibly small seed of existence. As the singularity stirred, time exhaled its first breath. It unfolded softly, not in a violent rush, but in an elegant, inevitable expansion, as though reality had finally chosen to emerge from its long, quiet slumber. Dimensions began to open like petals of a cosmic flower, one unfolding into another, each adding depth and structure to a universe that had just begun to learn the meaning of becoming. Energy swirled, space stretched, and the first laws of physics whispered themselves into existence, subtle but unbreakable, a framework upon which everything else would depend. With that breath, the universe stepped out of its timeless cradle and into motion. The shift was delicate, yet its consequences were infinite. Space began to widen, temperature began to fall, and the first threads of matter began to take shape inside the newborn cosmos. And as you drift deeper into this moment, you may feel a faint widening within yourself, as though some ancient part of you remembers that your atoms were once part of this vast beginning, once warmed by the very first light the universe ever produced. Time had begun, and with it, the story of everything was ready to unfold. In the newborn universe, everything moved with a speed and intensity that defies comprehension. Space expanded not gently as it does today, but at a pace so extraordinary that distances which are now measured in billions of light years grew from microscopic scales in less than a heartbeat. Yet even in this fierce unfolding, there was something remarkably elegant, an underlying order guiding the chaos, as if the universe already knew the shape it wished to take. Temperatures soared far beyond anything that would ever exist again. A searing ocean of pure energy rippling through every corner of the expanding cosmos. There were no atoms, no particles, no structures of any kind, only radiant energy dancing in a brilliant, unbroken field. As this ocean expanded, it cooled, not quickly and not evenly, but gradually falling just enough for energy to begin transforming into the first building blocks of reality. Photons streamed freely, unbound by matter, forming what would later become the faint afterglow of creation itself. Quarks flickered into existence and vanished just as quickly, obeying laws that had only moments earlier begun to define themselves. These quarks, unable to remain alone in such violent conditions, found each other and fused into tiny, fragile combinations, the earliest seeds of protons and neutrons. Their existence was brief, flickering between order and dissolution, yet every one of them carried within it the possibility of a future star, a future ocean, a future life. The universe was still far too hot and too dense for light to escape. Every photon collided with charged particles, bouncing, scattering, trapped in a glowing, turbulent fog. And yet this light, though imprisoned, held a memory, a record of the universe's infancy that would one day stretch across the sky as a soft, ancient whisper. Physicists call it the cosmic microwave background, but in truth it is something far more poetic, the first breath of light preserved across billions of years. As expansion continued, the chaotic energy slowly softened, becoming less violent, less blinding. The pressure eased, the density dropped. A great cosmic rhythm began to emerge, one that would guide matter into new forms, new structures, new possibilities. It was as if the universe, still very young, had taken its first step from pure energy toward the promise of complexity. Nothing yet resembled the stars or galaxies we know today, but the ingredients were gathering. The canvas had been stretched, the paint had been chosen, the first strokes, gentle, delicate, inevitable, were beginning to appear. And as you sink deeper into this unfolding story, you may notice a quiet sense of grounding within yourself, a calm awareness that everything around you, including you, was born from this same soft glow. The light that filled the early universe still moves through the atoms in your body, still echoes in the spaces between your thoughts. You are, in a very real way, made of this first breath of light. As the universe continued to expand, the furious brightness of its earliest moments slowly dimmed into something calmer, something cooler, though still unimaginably hot by any standard we know today. The violent chaos of pure energy began to settle, giving room for structure to emerge. For the first time, matter had the chance to linger rather than dissolve instantly back into energy. It was here, in this delicate shift, that the cosmos passed a quiet threshold, the moment when existence gained weight, when particles learned to remain. Quarks, those tiny, restless fragments of the universe, no longer flickered in and out of reality as quickly as they appeared. Instead, they clung to one another, binding into triplets that formed the very first protons and neutrons. This process was anything but peaceful. It happened in currents of tremendous heat and pressure, within a sea of constant collisions and wild transformations. Yet somehow, amid all that turbulence, these fragile combinations persisted. Each proton was a victory against dissolution, a promise that the universe was becoming stable enough to hold on to itself. But even as protons and neutrons formed, they drifted alone through the expanding cosmos. Electrons, light and agile, zoomed freely between them, unable to bond. Temperature was still too high for anything resembling an atom. So the universe remained a glowing, particle-rich cloud. Beautiful but chaotic, like a mist of sparks suspended in a storm. Light still could not travel freely, trapped within this thick plasma, bouncing endlessly between charged particles. If you could have witnessed it, you would have seen something like a shimmering fog of energy, dazzling, restless, alive. Still, the gradual cooling continued. What once happened in fractions of a second now unfolded over minutes, then hours. This slow shift gave space for new forms of order. Protons and neutrons began to combine into slightly larger structures. The first simple nuclei. Hydrogen emerged, first light, abundant, and destined to become the fuel of future stars. Then helium, forming in tiny clusters that glowed with the warmth of their creation. A trace of lithium, too, joined the cosmic mixture. In these early moments, the chemical foundation of the universe was quietly written, not with intention, but with the gentle guidance of physics shaping possibility. This stage, known as primordial nucleosynthesis, lasted only a few minutes, yet it determined the composition of the cosmos for billions of years to come. Imagine that. In the earliest heartbeat of time, the universe chose the ingredients that would become galaxies, suns, oceans, and life. Almost everything you see around you today can be traced back to those few minutes after the Big Bang, when matter learned to remain and the cosmos took its first step toward complexity. And as you absorb this moment, you may feel a deep sense of continuity, an awareness that the atoms in your body were forged in the same quiet furnace, carried forward through every era of cosmic history. You are not separate from this story. You are made of it. Your breath, your heartbeat, your memories, all built on the particles that were born in these first, simple moments of creation. As the universe continued to stretch and cool, its early turbulence softened into something remarkably calm. What had once been a dense, glowing fog of charged particles was now beginning to thin, allowing space to open and temperatures to fall. Every second brought a subtle shift, slower collisions, gentler interactions, and a growing stability that made new forms of order possible. Yet, despite this progress, the universe was still shrouded in a radiant haze. Light remained trapped, bouncing endlessly from particle to particle, unable to travel freely. It was a cosmos without visibility, without clarity, without the kind of openness that would allow structure to truly emerge. But cooling is a patient sculptor. As temperatures continued to decline, protons and electrons, once too energized to remain together, finally began to settle into one another's embrace. Slowly and almost tenderly, they formed the first true atoms. Hydrogen came together, first in vast numbers, followed by helium, each neutral atom acting like a small island of calm in a sea that had been boiling for hundreds of thousands of years. With electrons now bound instead of loose, the universe underwent a profound transformation. It lost its opacity. This moment, known as recombination, marked a turning point so gentle and yet so monumental that it is often described as the universe's first moment of clarity. For the first time, photons, those restless beads of ancient light, were no longer imprisoned. They slipped free from the tangle of charged particles and began traveling across space without obstruction. These photons had been moving ever since, their wavelengths stretching as the universe expands, cooling into the faint, low-energy glow we now call the cosmic microwave background. If you could watch this transition unfold, you would witness something breathtaking. The universe, once glowing with a blinding brilliance, suddenly becoming transparent, almost like a mist clearing to reveal a vast, open landscape. This was the moment when the cosmos became visible to itself. The fog thinned, the light escaped, and the universe entered a new stage of existence, clear, calm, and ready to evolve. But the release of light was not just a visual transformation. It was emotional, in a way like the first deep exhale after holding your breath for far too long. The trapped energy that once churned in every direction now drifted outward in smooth, uninterrupted streams. And those streams still surround us today. Every time scientists capture the faint whisper of the cosmic microwave background, they are, in a sense, listening to the quiet sigh of a universe just beginning to understand its own shape. As you settle deeper into this unfolding story, you might notice a softness in your awareness, a feeling of spaciousness, as if your mind mirrors the transparency that the young universe once achieved. Just as the cosmos opened itself to light, you too may feel something within you gently opening, allowing a quiet clarity to settle in. The universe had taken its first clear breath, and in doing so, it set the stage for everything that would come next. With the universe now transparent and bathed in the gentle afterglow of released light, a new era began, one far quieter, far slower, and far more subtle than the violent birth that came before. Space continued to expand, but not with the overwhelming force of the early moments. Instead, it stretched with a steady calm, allowing the first delicate patterns to emerge. Though the cosmos appeared smooth and evenly spread, it was not perfectly uniform. Tiny fluctuations in density, so small they seemed almost accidental, were scattered throughout the fabric of space. And yet, these faint irregularities would become the blueprint for everything the universe would one day build. These small variations, colder here, warmer there, acted like gentle seeds drifting across a cosmic field. In slightly denser regions, gravity found something to hold on to. It pulled ever so softly, gathering invisible threads of matter toward these pockets of potential. Over millions of years, these threads thickened, creating delicate webs that stretched across the universe like faint, glowing filaments. This was the beginning of cosmic structure formation, a slow choreography guided not by chaos, but by gravity's quiet, persistent hand. Dark matter, mysterious, unseen, yet vastly abundant, played a central role in this process. Though it emitted no light and interacted with nothing except gravity, it formed enormous halos of invisible mass, shaping the scaffolding around which normal matter would gather. You might imagine it like a silent architecture, a vast lattice of unseen corridors and intersections, each guiding the flow of ordinary matter into clusters and rivers. These invisible frameworks became the cradle where future galaxies would one day ignite. As hydrogen and helium drifted through this gravitational landscape, they began pooling into these dark matter wells, gathering slowly, patiently, As though following an ancient map, space remained cold and dark, but the tension was growing a quiet pressure, a slow drawing in of matter that hinted at the next great transformation. Regions that were slightly denser than their surroundings continued to collapse, their gravitational pull strengthening as more material joined them. These regions grew heavier, tighter, more concentrated, preparing for a moment of ignition that had never before existed in the universe. If you could drift through this era, you would see none of the brilliance that defines the cosmos today. You would float through an immense, silent darkness, punctuated only by faint ripples of matter, thin streams flowing into dense knots, like the early sketch lines of a masterpiece not yet filled with color. And yet, within these quiet patterns lay the promise of light. The first stars had not formed yet, but their birth was coming. Space was gathering fuel, temperatures were rising, pressure was building, slowly and almost imperceptibly toward the threshold where creation would flare into brilliance once more. As you absorb this moment, you might sense a parallel inside yourself, a recognition that even in long stretches of quiet, the groundwork for profound transformation is quietly being woven. The universe was no longer a storm of energy or a fog of glowing plasma. It was becoming something intricate, structured, and full of potential. The seeds were in place. The darkness was ready to bloom. As matter continued to gather into the silent knots carved out by dark matter's invisible scaffolding, the universe drifted deeper into darkness. No stars shone yet. No galaxies lit the sky. The cosmic background glow faded with every passing million years, stretching into longer and colder wavelengths. It was a universe without color, without illumination, an enormous, tranquil night waiting for its first spark. But inside the densest regions, hydrogen gas was slowly being drawn inward by gravity, compressing tighter and tighter, as if the darkness itself were holding its breath in anticipation. As the collapsing clouds grew denser, the atoms within them collided more frequently, raising the temperature at their cores. Pressure built steadily, quietly, with a kind of cosmic patience. What began as gentle gatherings of gas became vast, swirling concentrations massive, heavy, and unstable. Gravity continued to squeeze them inward, trying to compact them into smaller and smaller volumes. Eventually, deep in the heart of these collapsing clouds, temperatures climbed to millions of degrees. Hydrogen atoms were forced so close together that their natural repulsion broke down, allowing them to merge. And in that moment, something happened that had never occurred before in the history of the cosmos. Nuclear fusion began. The first stars ignited. Their birth was not violent but radiant, an awakening, a sudden emergence of light in a universe that had known only darkness for hundreds of millions of years. These early stars, called Population 3 stars, were nothing like the stars we know today. They were enormous, many hundreds of times the mass of our sun, burning with a fierce blue-white brilliance that poured across the young cosmos. Their lifetimes were short, ending in spectacular explosions that forged the first heavy elements, carbon, oxygen, iron materials that would one day become the building blocks of planets, oceans, forests, and life. The appearance of these first stars transformed the universe. Darkness was no longer absolute. Light once again flowed across space, but this time it was not trapped or scattered. It traveled freely, illuminating the immense web of matter that gravity had sculpted. The early universe began to glow with a soft, ancient shimmer. Regions once cold and silent were now warmed by starlight, revealing the structure of cosmic filaments stretching across unimaginable distances. The darkness became a canvas, and the stars became its first strokes of light. If you could have floated through this cosmic dawn, you would have seen clusters of brilliant, massive stars shining together in loose groups, early star cities forming in the deep hollows of the cosmic web. Their intense ultraviolet radiation began to reionize the surrounding gas, slowly stripping electrons away and pushing back the remaining fog. This era, known as cosmic reionization, marks the moment when the universe fully awakened from its long night. The first stars were not merely sources of light. They were sentinels announcing the beginning of cosmic structure, the opening chapter of the universe as we now recognize it. And as you sink into this part of the story, you may feel a quiet warmth inside, a recognition that the atoms within your body were once illuminated by these very first stars. Their light, though long extinguished, left behind the elements that would eventually form everything you are. The universe was no longer dark, and neither was its destiny. The first fires had been lit, and from those fires, creation would begin to unfold in all its grandeur. With the first stars blazing through the primordial darkness, the universe entered a new chapter, one defined not just by isolated bursts of light, but by the slow, graceful organization of those lights into vast cosmic structures. The early stars did not remain alone for long. Their immense gravitational pull began gathering them into clusters, drawing gas, dust, and dark matter into deeper wells of attraction. What began as loose gatherings of starlight slowly tightened into rotating systems, delicate, swirling islands suspended in a sea of expanding space. These were the first galaxies, forming quietly, gently, like embers drifting into patterns within a darkened sky. The earliest galaxies were small, irregular, and unstable, far from the elegant spirals and giant ellipticals we recognize today. They flickered with intense brightness, fueled by stars far larger and hotter than any that now exist. Their shapes were uneven, almost chaotic, formed by the relentless condensation of matter into whatever structures gravity demanded. And yet, within this seeming disorder, a kind of cosmic harmony was emerging. Gas clouds spiraled inward, dark matter halos expanded outward, and stars born in violent bursts collected into luminous clusters that moved together like flocks drifting through a quiet ocean of night. As more stars ignited, their combined radiation began sculpting the space around them. Powerful stellar winds pushed gas outward, clearing pockets inside these young galaxies and making room for new generations of stars to form. Some galaxies merged with others, colliding in slow, majestic dances that took hundreds of millions of years to complete. These collisions, far from destructive, were creative events. They triggered waves of star formation that lit entire regions with fresh brilliance, shaping galaxies into larger, smoother structures. Over time, these early, clumpy galaxies evolved into the grand spirals and massive ellipticals that populate the universe today. If you could have drifted through this era, you would have witnessed breathtaking scenes, swirling clouds collapsing into stellar nurseries, bright clusters of newborn stars gleaming like scattered jewels, and dark matter halos silently guiding the motion of entire galaxies. You would see streams of stars stretching between merging galaxies, delicate bridges of light that formed during their long gravitational embrace. Space was still expanding, but within its expansion, beauty was slowly crystallizing, structure rising from simplicity, complexity blooming from the raw ingredients of the Big Bang. These early galaxies played a profound role in shaping the future. Their stars forged heavier elements in their cores: carbon, nitrogen, oxygen, silicon, iron, each created through the intense pressures of nuclear fusion. When these stars ended their lives in colossal explosions, they scattered these elements into the interstellar medium, enriching the gas that surrounded them. The universe, once made almost entirely of hydrogen and helium, was becoming more diverse, more capable of forming planets, atmospheres, oceans, and eventually life itself. Every breath you take today, every molecule in your bones, every spark of thought in your brain can be traced back to these early galaxies, to the stars that lived and died within them. As you let yourself sink into this moment, you might sense the immensity of the journey that the universe has already taken. From a single point of infinite density to vast webs of galaxies spanning billions of light years, to the atoms inside your body, shaped by ancient stars. The cosmos was no longer a dark, simple expanse. It had become rich, textured, and luminous. And this growing structure, this grand, unfolding architecture, was only the beginning of an even deeper story. As galaxies formed, merged, and matured, the universe itself continued its vast, steady expansion, a movement so gentle and so persistent that it shaped every corner of reality. This expansion did not push galaxies through space like drifting ships on an ocean. Instead, space itself stretched, carrying galaxies with it as though they were delicate lights painted on an ever-widening canvas. To an observer floating in this early cosmos, the transformation would feel subtle at first, almost undetectable. But over millions and billions of years, the effect became profound. The universe grew larger, colder, and more spacious, allowing new realms of structure to unfold. What guided this expansion was not simply momentum from the Big Bang, but a mysterious force woven into the fabric of space: dark energy. Invisible, silent, and persistent, dark energy acted like a gentle pressure that pushed the universe outward. At first, its influence was small compared to the immense gravitational pull of matter. But as the cosmos expanded and matter thinned, dark energy's presence became more dominant. Galaxies that once drifted near one another began moving apart more quickly, as if space were quietly accelerating beneath their feet. Over time, this accelerating expansion became the defining motion of the universe, shaping its ultimate fate. Inside galaxies, however, gravity still reigned supreme. Stars orbited their galactic centers, gas clouds spiraled into tight arms, and dark matter halos held everything together in a delicate balance. These internal structures resisted the expansion, maintaining their forms even as the vast distances between galaxies grew. If you were drifting inside a galaxy during this era, you wouldn't feel the expansion at all. Everything around you, the stars, the dust, the stellar nurseries, would remain bound in a gravitational embrace. It was only when you looked outward to the spaces between galaxies that you would see the true scale of the cosmic dance unfolding. As space stretched, light traveling across it stretched as well. Waves that began as brilliant ultraviolet radiation lengthened into visible light, then into infrared, and eventually into faint, cold microwave signals. The deeper into the universe you looked, the older the light became, each photon carrying a quiet message from a time when galaxies were young and stars were still learning their rhythms. This stretching of light, known as cosmic redshift, became the universe's way of recording its own history, weaving the passage of time into the fabric of the cosmos. The accelerating expansion had another profound effect. It gradually isolated galaxies from one another. Over billions of years, clusters remained gravitationally bound, but vast regions of space between them expanded so quickly that galaxies drifted beyond the reach of light itself. Entire classes of galaxies slowly disappeared from one another's observable horizons, not because they ceased to exist, but because space had stretched so far and so fast that their light could no longer bridge the growing gap. The universe was becoming a collection of island realms, each galaxy or galaxy cluster living within its own gravitational pocket, surrounded by an ocean of expanding darkness. And yet, in this immense and growing separation, there was a deep, serene beauty. Expansion gave the universe room to breathe, room to evolve, room to grow more intricate. It allowed galaxies to form without constant collision, allowed stars to live full lifetimes, allowed planetary systems to arise from quiet disks of dust. The universe was not rushing, it was unfolding, taking its time, shaping itself in patient, sweeping motions across billions of years. As you drift into this part of the story, you may feel a sense of spaciousness within yourself, a gentle widening, as though your thoughts have more room to settle. The universe was expanding, yes, but it was also calming. From the fierce brilliance of the Big Bang to the slow, graceful dance of galaxies, the cosmos was learning to balance creation with stillness. And within that balance, the seeds of future worlds were quietly preparing to form. As the universe settled into its grand architecture of galaxies and expanding space, the next great transformation began not in vast cosmic voids, but deep within the blazing hearts of stars. These stars, descendants of the first luminous giants, had grown more stable, more complex, and more capable of shaping the ingredients from which all future planets and life would emerge. Inside their cores, unimaginable pressures and temperatures created environments unlike anywhere else in the cosmos. Here, the universe continued its story of creation in a quieter, more intimate way, by forging the elements that would one day compose everything familiar. Hydrogen, the simplest and most abundant element, remained the primary fuel of stars. Through the steady process of nuclear fusion, hydrogen atoms were pressed together deep in stellar cores until they combined into helium, releasing vast amounts of energy in the form of light and heat. This energy radiated outward, pushing against the inward pull of gravity and allowing stars to maintain their delicate equilibrium. It was this calm balance, gravity pressing inward, fusion pushing outward, that allowed stars to shine stably for billions of years, acting as steady, glowing furnaces across the night. As stars aged and their hydrogen supplies dwindled, their cores contracted and temperatures rose to even more extreme levels. This new heat triggered the fusion of heavier elements, beginning with helium and moving upward through carbon, oxygen, neon, and beyond. Each stage of fusion required greater pressure and temperature, pushing stars closer to their limits. In these fiery depths, the universe was crafting the fundamental ingredients of life: the carbon that forms the backbone of every molecule in your body, the oxygen that fills your lungs, the calcium in your bones, the iron in your blood. All of it forged in the hearts of long extinguished stars. But even the most massive stars had a limit. When they exhausted their final reserves of fusible material, their delicate balance collapsed. Gravity gained the upper hand, crushing the core with staggering force. In an instant, the star's inner layers imploded only to rebound outward in a colossal explosion known as a supernova. This violent release of energy blasted newly forged elements into the surrounding galaxy, scattering them across interstellar space. In these brilliant, catastrophic moments, the universe became enriched with the raw materials that would later form rocky planets, atmospheres, oceans, and eventually the chemistry of life. The aftermath of these explosions left behind swirling clouds of enriched gas and dust, vast nebulae shimmering with the stardust of previous generations. New stars and planets would one day form from this material, carrying within them the ancient signatures of long-gone stellar ancestors. If you could have floated through such a nebula, you would have seen a landscape of glowing filaments and drifting clouds, illuminated by young stars forming within them. You would see the recycling of cosmic material, the endless cycle of matter moving from star to space, from space to star, shaping the history of the universe with every transformation. And as you let yourself drift into this chapter of the cosmos, you might feel a quiet sense of belonging. The iron in your blood was forged at the center of a collapsing star. The calcium in your bones was born from stellar ash. The oxygen you breathe once glowed inside a star that died billions of years before Earth existed. You are not merely in the universe, you are made of its oldest memories, shaped by processes that began long before life ever formed. In this way, the story of stars is also your story, woven across unimaginable stretches of time. As generations of stars lived and died, the universe transitioned from a simple composition of hydrogen and helium into a far more intricate chemical landscape. With each cycle of stellar birth and stellar death, the periodic table expanded across the cosmos. What began as a universe with only a handful of elements was slowly transformed into one filled with dozens, each forged through specific, extraordinarily precise physical processes. This deepening chemical complexity set the stage for everything that would later emerge: planets, atmospheres, oceans, and the molecular structures that make life possible. Inside stars, the progression of fusion followed a well-defined path governed by quantum mechanics. As temperatures rose beyond 100 million degrees, helium nuclei fused through the triple alpha process to produce carbon, a reaction delicate enough that a slight difference in nuclear resonance levels would have prevented carbon from forming at all. The universe, in a sense, balanced on a razor's edge of physical constants, each finely tuned to allow complexity to blossom. From carbon, stars built oxygen and neon, each step requiring higher temperatures and denser cores. These reactions occurred only in stars massive enough to achieve such extreme conditions, meaning that the chemical richness of the universe depended on the lives of these rare and powerful giants. As fusion progressed up the periodic table, the path eventually reached iron, an element with a unique nuclear property. Iron's nucleus is so tightly bound that fusing it requires more energy than it releases. At this point, stellar fusion halts. The star, deprived of outward pressure, collapses under its own immense gravitational weight. What follows is one of the most energetic events in the cosmos: the core collapse supernova. Within fractions of a second, the collapsing core rebounds, driving shockwaves outward at nearly 1/10 of the speed of light. In this furious environment, temperatures spike above 1 billion degrees, enabling rapid neutron capture processes, the R process that forged the universe's heaviest elements: gold, platinum, uranium, and dozens more. These heavy elements did not form gently. They were created in places where matter was squeezed to neutron-dense extremes, either in supernovae or, even more dramatically, in collisions between neutron stars. Such mergers, rare but immensely powerful, unleashed gravitational waves that ripple across space-time, leaving signatures modern observatories can detect. In these collisions, the R process operates with extraordinary efficiency, building some of the heaviest stable nuclei known. Without these cataclysmic events, the universe would lack the very materials that compose our technology, our geology, and even the biochemical processes that sustain life. Once released into the interstellar medium, these elements mixed with clouds of hydrogen and helium, creating chemically diverse nebulae. Over millions of years, turbulence, magnetic fields, and gravity shaped these nebulae into dense molecular clouds, the birthplaces of new stars and planetary systems. Here, chemistry extended beyond atoms. Under the right conditions, carbon, oxygen, nitrogen, and hydrogen combined into simple molecules: water, carbon monoxide, methane, ammonia. These molecules cooled the clouds more efficiently than atoms alone, allowing gas to collapse further, forming disks around newborn stars. Within these disks, protoplanetary chemistry emerged: dust grains coated with ices, organic compounds forming on their surfaces, complex molecules drifting through the growing planetary nurseries. If you could observe this process up close, you would witness a universe that is not simply expanding, but evolving chemically with astonishing precision. You would see each step governed by laws so consistent and elegant that they produce the same elements, the same molecules, the same building blocks anywhere in the cosmos. From the heart of a collapsing star to the surface of a nascent planet, chemistry became the silent architect of structure, enabling not just the formation of rocky worlds, but eventually the emergence of biological systems capable of thought, memory, and awareness. And as you reflect on this, you might feel a deep connection to the physical laws that shaped you. Every atom in your body followed this sequence. Hydrogen born in the Big Bang, carbon forged in a giant star, iron produced in a supernova, trace elements created in neutron star collisions. You are, in every measurable sense, a product of cosmic chemistry, an arrangement of particles shaped by billions of years of astrophysical evolution. As the universe enriched itself with heavier elements, the interstellar medium transformed from a thin, simple gas into a complex mixture of atoms, molecules, charged particles, and micron-sized grains of dust. These dust grains, tiny fragments of carbon, silicates, ices, and metals, became the quiet engineers of the next cosmic chapter, the formation of planets. Without them, stars would still form, but the worlds that orbit those stars, the solid surfaces, the oceans, the atmospheres, the chemistry of life itself, none of it could exist. And so, in the cooling arms of the universe, cosmic dust began its subtle but essential work. When a massive molecular cloud collapsed under gravity to form a new star, it did not collapse symmetrically. Even the slightest rotation, just a trace of angular momentum, caused the material to flatten into a swirling disk called a protoplanetary disk. At the center of this disk, temperatures soared, igniting nuclear fusion and giving birth to a new star. But farther out from the center, temperatures dropped sharply. Dust grains drifting through the disk found one another, sticking together through electrostatic forces, like sparks clinging in the dark. Over time, these microscopic particles accumulated into larger clumps, millimeter-sized pebbles, then centimeter-sized stones, then meter-sized boulders. This stage, governed by coagulation and accretion, unfolded with both delicacy and violence. Dust collisions had to be gentle enough to allow particles to stick, yet energetic enough to compact them into larger aggregates. As these growing bodies moved through the disk, they experienced gas drag, losing angular momentum and spiraling inward, where they collided and merged with other bodies. It was a slow but relentless process, shaping the raw ingredients of planets within a few million years. Eventually, these aggregates grew into planetesimals, bodies kilometers across, massive enough for gravity to become the dominant force binding them. From here, growth accelerated dramatically. Planetesimals collided and merged through gravitational focusing, their mutual attraction increasing the probability of impact. Some grew into planetary embryos, dozens to hundreds of kilometers in size. The largest of them, called protoplanets, cleared their orbital paths, sweeping up smaller debris in a process known as dynamical clearing. Meanwhile, the composition of forming planets depended critically on their location within the disk. Close to the star, high temperatures prevented volatile compounds like water and methane from condensing. Here, rocky planets formed dense worlds built from silicates, iron, and metal oxides. Farther from the star, beyond the frost line, temperatures were low enough for ices to accumulate. This allowed the formation of massive icy cores that could rapidly accrete hydrogen and helium from the surrounding gas, becoming gas giants. In this way, a disk just a few hundred astronomical units wide differentiated into a family of worlds, each shaped by temperature, chemistry, and gravity. If you could observe a protoplanetary disk from within, you would witness a dynamic environment, spiraling dust lanes, shock fronts, vortices trapping grains into dense rings, and newborn planets carving gaps in the disk as they orbited. You would see collisions that shattered bodies into fragments, and fragments that recombined into larger forms. You would feel the heat of the central star, the cold of the outer disk, and the quiet gravitational tug-of-war unfolding across billions of kilometers. It would look chaotic, but beneath the surface, the laws of physics were orchestrating a steady, predictable evolution toward planetary architecture. As the disk aged, stellar winds and radiation from the young star gradually dispersed the remaining gas. What remained was a system of rocky planets, gas giants, dwarf planets, moons, asteroids, comets, and countless fragments, each a record of the processes that shaped them. In our own solar system, these processes gave rise to Earth, a planet whose chemistry and position would eventually permit life to emerge. But the same processes happened around stars across the galaxy, producing countless worlds, some barren, some icy, some perhaps temperate and rich with oceans. And as you consider this vast process, you might recognize something profound. Planets are not rare accidents. They are a natural consequence of star formation, emerging wherever conditions allow dust to settle and gravity to sculpt. Every world, including your own, began as a grain of cosmic dust floating in the aftermath of ancient stars. From that dust came continents, oceans, weather, ecosystems, and eventually minds capable of understanding the very universe that created them. As planetary systems matured and the last remnants of their natal gas disks faded into surrounding space, the universe entered an era marked by increasing stability and structure. Galaxies that once flickered with the chaotic light of massive newborn stars settled into more regular patterns. Spiral galaxies refined their sweeping arms. Elliptical galaxies grew dense and smooth. Clusters of galaxies assembled into gravitationally bound cities of starlight. Beneath these visible structures, an even deeper order emerged, one sculpted by the invisible geometry of dark matter and the accelerating stretch of space-time itself. Within galaxies, stars moved along orbits shaped by a delicate interplay of mass distribution and gravitational potential. Gas clouds drifted in slow, grand cycles, collapsing to form new stars, which in turn enriched the galaxy with heavier elements when they died. Over billions of years, these cycles repeated, gradually transforming simple hydrogen-rich galaxies into chemically diverse ecosystems. Regions heavy with metals became fertile grounds for rocky planet formation, while broader galactic dynamics, stellar migration, gravitational resonances, and tidal interactions spread elements across vast distances. The interplay of physics and time gave galaxies not just form, but memory. On even larger scales, galaxies were not isolated structures but nodes in the cosmic web. Dark matter filaments stretched across hundreds of millions of light years, creating highways along which galaxies clustered and merged. Observations show that these filaments guide matter with exquisite precision. Galaxies flow along them like streams moving through carved channels. The resulting network resembles a vast neuronal structure, with clusters acting as hubs and filaments forming the connective tissue of the cosmos. This architecture did not arise from randomness, but from the small density fluctuations present in the universe's earliest moments, amplified by gravity's persistent, uncompromising pull. Within these clusters, galaxies frequently interacted, sometimes gently through tidal forces, other times through direct mergers. Contrary to how it might seem, these mergers were not destructive in the human sense, they were creative. When two galaxies collided, their stars rarely physically struck one another, given the enormous distances between them. Instead, gravitational forces stirred their gas, triggering waves of star formation that illuminated the newly merged system. These interactions reshaped galactic trajectories, redistributed angular momentum, and gradually built the massive galaxies we observe today. Even our own Milky Way bears scars of ancient mergers etched into the motion of its stars. Meanwhile, dark energy continued to drive the expansion of space, accelerating the pace at which galaxies drifted apart. Over billions of years, this expansion isolated galaxy clusters from one another. Light from the most distant galaxies grew stretched and faint, eventually slipping beyond the observable horizon. The universe, once densely connected, became a mosaic of gravitationally bound islands separated by oceans of expanding void. Yet within each island, each galaxy cluster gravity maintained order, protecting its internal structure even as space around it expanded relentlessly. This emerging balance between gravitational structure and cosmic acceleration defined the universe's large-scale behavior. Gravity gathered matter into stars and galaxies. Dark energy stretched the fabric of space, Nuclear fusion forged elements, collisions redistributed them, and chemistry built the foundations for future complexity. Across every scale, from the subatomic interactions inside stars to the motion of entire galaxies, order emerged from fundamental laws, consistent across time and space. If you allowed your awareness to drift across this vast tableau, you might sense a profound calm behind the apparent complexity. Every star, every planet, every arc of starlight obeys the same principles: gravity shaping orbits, thermodynamics guiding heat flow, quantum mechanics determining atomic structure. The universe, though vast and often chaotic in appearance, moves with an underlying coherence, an elegant, almost meditative rhythm that connects the smallest particles to the largest cosmic structures. And as you settle into this understanding, you may feel a deep resonance within yourself. The same physical laws that shape galaxies also shape your neurons. The same elements forged in ancient stars course through your bloodstream. The universe is not something separate from you, it is a continuous system, and you are one expression of its unfolding order. Every breath you take is connected to this cosmic evolution. Every thought a ripple in a lineage that began with the first atoms formed after the Big Bang. As billions of years passed, the universe moved steadily from its turbulent youth into a calmer, more mature phase. Expansion continued, stretching space-time ever outward, but the frenetic pace of transformation slowed. The temperature of the cosmos dropped with each passing epoch, falling from millions of degrees in its early days to just a few degrees above absolute zero in the vast intergalactic voids. This long cooling, measured not in centuries or millennia but in billions of years, became one of the most defining processes in cosmic history, shaping the evolution of galaxies, stars, and the fabric of space itself. Within galaxies, star formation began to shift. In the early universe, stars formed in enormous bursts, consuming gas at staggering rates and producing massive, short-lived suns that lived quickly and died violently. But as galaxies aged, their gas reservoirs dwindled. Much of the hydrogen had already been converted into stars or locked away in stellar remnants like white dwarfs, neutron stars, and black holes. The remaining gas grew warmer due to stellar winds, supernova shocks, and gravitational heating, making it harder for new stars to form. Star formation did not stop it, simply slowed, becoming more selective, more delicate, relying on rare pockets of dense, cool gas capable of collapsing under gravity. This shift had profound implications for cosmic evolution. With fewer massive stars forming, the universe produced fewer supernovae, the violent events responsible for enriching galaxies with heavy elements. As a result, the chemical evolution of galaxies also slowed. Future generations of stars would still contain the elements necessary for rocky planets and complex chemistry, but the pace of enrichment had shifted from a dramatic crescendo to a long, gentle sustain. Galaxies matured as star formation migrated from their chaotic cores to the calmer outskirts, where gas collected in spiral arms and slowly condensed into new stellar nurseries. On larger scales, galaxy clusters continued to grow through mergers, but these interactions became less frequent as expansion accelerated. The gravitational bridges that once drew distant galaxies together began to weaken. Regions of the universe that were once gravitationally connected slipped beyond one another's horizons, carried apart by the relentless push of dark energy. The universe's structure remained, but its connectivity slowly faded. Clusters became isolated islands of matter surrounded by vast, silent oceans of expanding space. Meanwhile, the cosmic microwave background, the oldest light in the universe, continued to cool, its wavelength stretching further into the infrared, then into the microwave, and eventually into radio frequencies over unimaginable spans of time. This fading glow, once brilliant enough to illuminate the entire sky, became increasingly faint, but never entirely disappeared. It remained the universe's most ancient whisper, a quiet memory of the moment when light first broke free from matter. If you drifted through the cosmos during this era of long cooling, you would feel the stillness of a universe settling into balance. Stars continued to shine, but their formation slowed. Galaxies rotated gracefully, their spiral arms gently sculpted by gravity. Clusters held tightly to their members, while the space between them grew increasingly empty. Even quantum processes played quieter roles. Particle interactions rarefied, and the density of radiation fell to near absolute minimal levels. And yet, within this growing calm, complexity flourished. Planets cooled and stabilized, atmospheres formed and thickened, and on at least one world, Earth life took root, evolving in ways that mirrored the universe's own gradual transformation. The cooling of the cosmos was not simply a decline in temperature, it was a shift in tempo. The universe was no longer defined by violent births and explosive deaths, but by slow refinement, subtle motion, and quiet stability. Across billions of years, this slow settling created the conditions for long-lived stars, habitable planets, and ecosystems capable of developing intelligence and consciousness. The universe, once a storm of pure energy, had become a cradle for complexity. And as you contemplate this era, you might sense a parallel within your own awareness. Just as the cosmos transitioned from chaos to calm, from explosive change to deep equilibrium, your mind may feel itself settling gently, steadily into a quieter depth. The universe teaches, through its very history, that creation is not always loud. Sometimes it unfolds in silence, in slow cooling, in the steady rhythm of enduring structures shaped over vast stretches of time. As the universe matured, one of its most influential architects remained completely invisible. Dark matter, undetectable through ordinary light, continued shaping the cosmos with a gravitational precision unmatched by any luminous structure. Though it emits no radiation and resists interaction with normal particles, dark matter constitutes nearly 85% of the universe's total matter. Without it, galaxies would not hold their shape, clusters would not remain bound, and the cosmic web, the vast network of filaments connecting galaxy clusters, would never have formed. In the earlier stages of cosmic history, dark matter seeded the universe with subtle density variations. These seeds, amplified by gravity over hundreds of millions of years, drew ordinary matter into their invisible wells. As stars and galaxies emerged, they arranged themselves according to these unseen contours, much like rivers filling the valleys carved by mountains. Even today, every galaxy, including the Milky Way, is embedded in a massive dark matter halo, a spherical cloud extending far beyond the furthest visible stars. This halo provides the gravitational scaffolding needed for galaxies to rotate without collapsing. The evidence for dark matter emerges from the motions of stars. In spiral galaxies, stars far from the center orbit at high speeds, yet visible matter alone cannot generate enough gravity to hold them in place. Something unseen anchors them, a halo of dark matter whose mass outweighs that of the galaxy's stars by factors of 5 or more. Observations of gravitational lensing, the bending of space-time itself, also reveal dark matter's presence. Massive clusters distort background light into arcs and rings, revealing the enormous invisible mass shaping their gravitational potential. Dark matter also determines the universe's fate on larger scales. It slows expansion locally, allowing clusters to form, while dark energy accelerates expansion globally. This interplay creates a delicate balance between growth and isolation. As time stretches forward, dark matter structures remain gravitationally intact, even as space around them expands faster and faster. The result is a future where galaxy clusters become gravitational sanctuaries, regions of stability floating in an ever-widening cosmos. If you could drift inside a dark matter halo, you would not see or feel anything in the conventional sense. There would be no color, no texture, no sound. And yet you would be surrounded by an invisible architecture, a gravitational landscape sculpted over billions of years. Stars would orbit according to this hidden geometry, spiraling in synchrony with a force that neither scatters light nor resists motion. Dark matter does not merely shape the universe, it defines its structure. And as you settle deeper into this understanding, you may feel the calm certainty of a universe guided by principles that are consistent, elegant, and patient. Dark matter reminds us that the most influential forces in the cosmos are often the ones we cannot see, shaping everything quietly, continuously, and with profound precision. As the gravitational webs of dark matter sculpted structure into the cosmos, another, even more mysterious force began to reveal its influence: dark energy, a phenomenon woven into the very fabric of space-time. Unlike dark matter, which gathers matter together, dark energy pushes space apart. Its effect is subtle over short distances, but becomes overwhelming on cosmic scales. Around 5 billion years ago, its influence surpassed that of gravity, causing the expansion of the universe to accelerate. This shift marked one of the most profound transitions in cosmic history, one that still shapes the universe's future. Dark energy remains enigmatic. It does not clump, does not form structures, and does not interact with matter in the traditional sense. Instead, it acts uniformly across space, exerting a negative pressure that drives expansion. The simplest explanation treats it as a property of the vacuum itself, a constant energy inherent to empty space. In this view, as the universe grows, so does the amount of vacuum, and therefore, so does the total amount of dark energy. More space leads to more expansion. More expansion creates more space, a self-amplifying cycle that accelerates the expansion of the cosmos. The evidence for this acceleration comes primarily from Type Ia supernovae, stellar explosions so uniform in brightness that astronomers use them as cosmic distance markers. When these explosions were observed in distant galaxies, they appeared dimmer than expected, indicating that the galaxies were farther away than models of constant expansion predicted. This discovery, made in the late 1990 seconds, revealed a universe not slowing down under gravity, but speeding up under the influence of a mysterious, pervasive force. This acceleration reshapes the cosmic landscape. Galaxies that are not gravitationally bound to one another drift apart at ever-increasing speeds. Eventually, distant galaxies cross the cosmic event horizon, a boundary beyond which light can no longer reach us. Over trillions of years, Only the galaxies within our local gravitational cluster will remain visible. Everything else will fade beyond sight, not because it ceases to exist, but because space expands faster than light can bridge the growing gap. Dark energy ensures that the universe's future is one of isolation. Galaxy clusters will endure, but the connections between them will dissolve. Structures within clusters will remain gravitationally stable, but the cosmic web will stretch thinner, its filaments fading as vast voids expand. The night sky of far future civilizations will look emptier, quieter, stripped of the distant galaxies that once filled it with points of ancient light. Yet there is a strange serenity in this cosmic fate. Dark energy does not tear galaxies apart or disrupt planetary systems. Its influence is gentle on local scales. Life can persist, evolve, and flourish in secluded corners of the cosmos for incomprehensible stretches of time. Stars will continue to shine for trillions of years, and even after they fade, new forms of energy and structure may emerge. If you allow your awareness to drift across this future landscape, you may sense the universe's slow transition into a more spacious, quieter existence. The cosmos is not rushing toward an abrupt end. It is gliding gracefully into a vast, expanding calm. Just as earlier epochs were defined by fire, fusion, and fierce gravitational collapse, this era is defined by gentle divergence, a slow stretching of space-time that carries galaxies into solitude. And as you breathe into this understanding, you might notice a quiet parallel within yourself, the way expansion creates room, the way space allows clarity, the way distance can bring calm. The accelerating universe is not chaotic, it is spacious. It is not violent, it is patient. And its long future unfolds with the same quiet inevitability that marks every chapter of cosmic history. As dark energy continued to stretch the universe and galaxies settled into gravitational sanctuaries, the story of the cosmos increasingly became the story of stars, their formation, evolution, and eventual demise. Stars are the engines of cosmic chemistry, the forges of heavy elements, the beacons illuminating the universe. But even they are subject to the slow cooling and dimming of cosmic time. Their fates, determined entirely by their mass, outline the next great transitions in the universe's long evolution. In galaxies like the Milky Way, star formation persisted, but at a declining pace. Dense molecular clouds, once abundant and dynamic, became rarer and more depleted. The stars born in this era tended to be smaller, longer-lived, and more stable than their massive volatile ancestors. These smaller stars, called red dwarfs, burn their fuel at a whisper compared to the brilliant blue giants of the early universe. A typical red dwarf can shine for trillions of years, far longer than the universe has existed so far. This means that the majority of all stars ever born in the cosmos are still burning today, quietly illuminating the darkening skies of aging galaxies. Larger stars, however, follow a different path. Sun-like stars, after exhausting their hydrogen fuel, expand into red giants, shedding their outer layers into colorful planetary nebulae, delicate shells of gas glowing from the heat of the dying core. What remains is a white dwarf, a stellar remnant composed primarily of carbon and oxygen, hot but no longer capable of fusion. Over billions of years, white dwarfs cool, eventually becoming dark, cold objects known as black dwarfs, though none yet exist because the universe is still too young. Massive stars, with 8 or more times the mass of the Sun, end their lives far more dramatically. After producing heavy elements up to iron in their cores, they collapse violently and explode as supernovae, scattering enriched material into space and leaving behind neutron stars or black holes. These stellar remnants, dense beyond comprehension, become gravitational anchors that influence their surroundings long after the luminous star is gone. Neutron stars merge, creating gravitational waves that ripple across space-time. Black holes drift through galaxies, feeding occasionally on gas or stars that wander too close. Over time, as gas supplies dwindle and galaxies exhaust their reservoirs for new star formation, the universe enters what astrophysicists call the stelliferous era, an epoch defined by the long lifetimes of small stars and the gradual fading of stellar light. In trillions of years, massive stars will have vanished entirely, and red dwarfs will dominate the cosmic landscape. Their slow, steady glow will be the primary source of light in a universe that continues to expand and cool. If you could drift across a galaxy in this distant future, you would find it quieter, more diffuse, and filled with older stars. The brilliant clusters of earlier epochs would be gone, replaced by faint red points scattered across an increasingly dark sky. Star formation regions, those bright nurseries where gas collapsed into new suns, would be rare, isolated, and small. Much of the interstellar medium would have been swept into stars, locked away forever in compact remnants. Yet this era is not bleak, it is serene. Even as starlight becomes rarer, the universe's structure remains stable. Planets continue to orbit their stars. Stellar remnants drift like ancient monuments to earlier cosmic ages, and a vast, intricate ballet of gravity continues to unfold across galaxies, star systems, and clusters. As you sink into this vision, you may sense a profound calm, an awareness that even as the universe cools and dims, it retains its coherence, its structure, its slow and quiet beauty. Cosmic evolution is not only about creation, it is about transformation, endurance, and the long arc of time shaping everything into gentler forms. The stars, once fierce and brilliant, evolve into quiet embers, and the universe follows their lead, entering an era of patient, measured light. As the universe slipped deeper into the stelliferous era, the cosmos gradually shifted from a realm dominated by living stars to one increasingly shaped by their remnants, the dense, long-lasting objects left behind after nuclear fusion ceased. These remnants, white dwarfs, neutron stars, and black holes became the quiet custodians of cosmic history, holding within their compact forms the memories of earlier epochs when galaxies blazed with youthful light. Over billions and trillions of years, they would come to define the structure, dynamics, and energy flow of the aging universe. White dwarfs, born from the gentle deaths of sun-like stars, formed the most common stellar remnant. Composed primarily of carbon and oxygen in a crystalline lattice, they shine at first with the leftover heat of their former cores. Though they no longer fuse elements, they radiate slowly, cooling over billions of years. Their glow fades from bright white to red, then to infrared, and eventually into darkness. Over unimaginable lengths of time, longer than any star has yet lived, a white dwarf will cool completely, becoming a black dwarf, a cold, lightless remnant. These objects, though inert, remain gravitationally influential, continuing to anchor planetary systems and shape stellar neighborhoods. Neutron stars, by contrast, are monuments of cosmic violence. Born from supernova explosions, they are composed almost entirely of neutrons, packed so densely that a teaspoonful would weigh billions of tons. Their magnetic fields are trillions of times stronger than Earth's, and their rotation can reach hundreds of times per second. Over time, these pulsars slow and dim, their beams of radiation weakening as energy dissipates into space. Yet neutron stars are astonishingly stable and may persist long after most of the universe's luminous activity has faded. Occasionally, two neutron stars collide, forming black holes and releasing bursts of gravitational waves, ripples in space-time that continue to echo across the cosmos. Black holes, the most mysterious of stellar remnants, play an increasingly dominant role as the universe ages. Formed from the collapse of massive stars or through the merging of compact objects, black holes consume material that drifts too close, growing slowly over billions of years. At the centers of galaxies, supermassive black holes, millions to billions of times the mass of the Sun, anchor galactic motion. They shape the evolution of their host galaxies through jets, radiation, and gravitational influence. Even as starlight fades across the cosmos, these enormous structures persist, silent and enduring. As stellar remnants accumulate, the character of galaxies transforms. Where young galaxies shine with star-forming regions and bright clusters, aged galaxies become dominated by faint red stars, dim white dwarfs, and compact remnants drifting through vast reaches of nearly empty space. Collisions between stars become exceedingly rare, but gravitational interactions continue subtly sculpting the architecture of stellar systems. Over trillions of years, remnants exchange energy through gentle encounters, redistributing momentum and gradually altering their orbits within galactic halos. The interstellar medium, once rich with gas and dust, grows thin as star formation slows and remnants lock material away. With fewer new stars igniting, galaxies take on a quiet, almost contemplative beauty. Their spiral arms fade, their colors shift toward red, and their dynamics come to be governed by the long-term ballet of dark matter and stellar skeletons. In this era, gravity rather than light becomes the primary architect of cosmic structure. If you could drift through a galaxy in this distant future, you would see a sky filled with fewer bright stars but abundant with faint embers and silent remnants. White dwarfs, cooled into darkness, would pass unnoticed. Neutron stars would drift like compact shadows. Black holes would lurk as invisible wells, detectable only through their gravitational influence on nearby bodies. The galaxy would feel stable, ancient, and deeply serene, a structure shaped not by creation, but by endurance. And as you rest within this vision, you may feel a parallel within yourself. Just as the universe transitions from fiery brilliance to quiet longevity, there is a similar rhythm in human experience, a recognition that meaning does not always come from brightness or intensity, but from persistence, continuity, and the steady unfolding of existence. The stellar remnants, silent, enduring, timeless, remind us that even in the softest light, the universe continues its story. As the universe continued to age, the grandeur of galaxy formation gradually gave way to a slower, more deliberate cosmic choreography. Galaxies, once vibrant with blue, luminous, star-forming regions, now transitioned into quieter, more stable forms. Their spiral arms softened, their colors reddened, and the chaotic dynamism of their youth settled into the serene, long-term evolution dictated almost entirely by gravity. In this era, galaxies no longer grew rapidly or underwent explosive bursts of light. Instead, they drifted, merged, and slowly reshaped one another through gravitational tides and gentle interactions extending across billions of years. Within galaxy clusters, where thousands of galaxies orbited a shared center of mass, the gravitational landscape changed subtly but continuously. Galaxies passed each other like ships in a vast, dark ocean, their motions influenced by the invisible pull of dark matter halos. Sometimes they grazed one another, exchanging stars and altering their orbits. Other times, they collided and merged, forming larger, more massive structures. These mergers were not sudden or violent in the way human eyes might imagine. They unfolded over hundreds of millions of years, with stars passing gracefully through one another due to the immense distances between them. When two galaxies merged, their dark matter halos interpenetrated first, blending like overlapping gravitational clouds. The stars followed, settling into new orbits as their collective momentum redistributed. Gas clouds compressed during the interaction, triggering brief bursts of star formation pockets of renewed light against the backdrop of an increasingly dim universe. Over time, the chaotic motions of stars settled into equilibrium, forming a new galaxy often larger and more rounded than its predecessors. Many elliptical galaxies observed today are the relics of such ancient mergers. As mergers accumulated, galaxy clusters themselves grew denser and more massive. Their gravitational wells deepened, capturing stray galaxies drifting through intergalactic space. Supermassive black holes at the centers of galaxies also grew dramatically during these interactions, fed by inflows of gas and dust stirred up by gravitational tides. Some of these black holes emitted jets of high-energy particles, briefly illuminating their surroundings before settling once more into quiet, persistent gravitational anchors. Beyond the bright cores of clusters, however, the universe was changing in a different direction. The accelerating expansion driven by dark energy stretched the vast voids between galaxy clusters to enormous sizes. Over time, clusters that were once gravitationally connected drifted beyond one another's cosmic horizons. Their light could no longer traverse the ever-widening gulf of space. The large-scale cosmic web, the intricate network of filaments connecting all matter, began to thin. Filaments elongated, weakened, and eventually became gravitationally isolated islands, drifting through expanding darkness. Within these isolated clusters, internal structure continued to evolve. Stars orbited calmly, remnants accumulated, and galaxies settled into stable configurations dominated by old stellar populations. Gas supplies dwindled, and without fresh infall from cosmic filaments, star formation slowed to a mere trickle. The night skies of worlds, should any civilizations exist in these distant times, would show a universe far quieter than the one we see today. A handful of nearby galaxies glowing faintly, without the distant background tapestry that currently fills our telescopes with billions of galaxies. If you drifted across such a galaxy in this era, you would feel the deep stillness of a universe that has entered its contemplative phase. Gravity continues its patient work, guiding stars and remnants into ever more refined orbits. The interactions that once sculpted entire galaxies now play out in slow motion, their timescales stretching into trillions of years. The cosmos, once young and fiery, has matured into a realm defined by longevity, stability, and the quiet persistence of structure against an ever-expanding background. And as you reflect on this, you might sense that cosmic evolution mirrors a profound truth. With time, intensity settles into depth. The universe's early brilliance, gave rise to the quiet resilience of galaxies and remnants that endure for eons. The slow dance of gravity, soft, persistent, and endlessly patient, becomes the guiding rhythm of an aging cosmos, just as your own awareness may find a deeper stillness as you journey further into this unfolding story. As trillions of years passed, the universe entered a phase where the creation of new stars became increasingly rare. The processes that once ignited brilliant stellar nurseries, dense clouds collapsing under gravity, enriched by the chemistry of earlier generations, began to fade. Galaxies that had once sparkled with the blue light of young stars now grew dimmer, settling into warm hues of red and gold. The cosmic era of vigorous star birth gave way to one of graceful decline, governed by the dwindling availability of cold, dense gas. Star formation requires a delicate balance of cooling, compression, and gravitational instability. In the early universe, these conditions were abundant. Gas was plentiful, temperatures fluctuated dramatically, and turbulent interactions between galaxies triggered new waves of collapse. But as time stretched onward, the cosmic environment changed. Gas became hotter and more diffuse, scattered by supernova explosions, stellar winds, and the heating effects of growing supermassive black holes. Much of the material capable of forming stars had already been locked away, either in long-lived red dwarfs that would shine for trillions of years, or in compact remnants that would never ignite again. The interstellar medium thinned. The spiral arms of galaxies, once marked by brilliant streaks of star-forming activity, faded as the raw materials needed to refresh them dwindled. Molecular clouds, the dense, cold cradles of new stars, became scarce. Their formation depended on conditions that were no longer common. Regions of low temperature, sufficient density, and shielding from harsh radiation. Without these ingredients, galaxies could no longer sustain high rates of stellar birth. In some regions, occasional star formation persisted, sparked by mergers or pockets of gas left undisturbed. But these episodes became increasingly rare. Even galaxy collisions, once powerful triggers of starburst events, lost their effectiveness as gas reservoirs diminished. Instead of igniting new stars, mergers often resulted in smoother, gas-poor elliptical galaxies with little capacity for further creation. Over time, the universe evolved into a realm dominated by aging stars and long-lived remnants. In this era, the stars that remained were overwhelmingly red dwarfs. Their slow-burning nature allowed them to outlive every other type of star, producing a soft, steady glow that illuminated their surroundings for trillions of years. If a civilization arose around one of these stars, its sky would lack the brilliant diversity of early cosmic epochs. Instead of a dense tapestry of starlight, it would see a sparse scattering of red points, stable, enduring, yet faint within the vast darkness. The galaxy itself would appear quieter, its once vibrant spirals having dissolved into diffuse halos of aging stars and dark matter. As star formation declined, the chemical evolution of galaxies slowed nearly to a halt. The heavy elements necessary for complex chemistry were already forged, but their further enrichment ceased. Supernovae became rare events, occurring only when the occasional massive star reached the end of its life. Over time, even these final bursts of element creation faded. The cosmic engine that had driven chemical diversity for billions of years sputtered to a near stop. Yet within this decline, there was stability. The absence of rapid, violent change allowed galaxies to persist in long-lasting equilibrium. Stellar remnants drifted undisturbed, planetary systems continued orbiting their quiet red suns, and gravitational structures remained coherent even as the universe around them stretched into emptiness. The cosmos was not dying, it was calming. Its creative frenzy had softened into a long, contemplative phase dominated by endurance rather than transformation. If you drifted through the universe at this time, you would feel its profound stillness. Vast regions of intergalactic space would appear utterly dark, broken only by the faint glow of distant red stars scattered across the void. The silence would be immense, yet gentle, an echo of the universe's long journey from fiery birth to quiet maturity. And as you settle into this vision, you might sense a deep resonance within yourself, the recognition that even decline can hold beauty, that quiet can hold meaning, and that the universe's slow rhythms are just as profound as its early brilliance. The cosmos, in its vast timeline, teaches that every phase, creation, evolution, stillness, carries its own quiet grandeur. As the universe moved deeper into its long, dimming future, the central role of luminous stars gradually shifted to the degenerate remnants they left behind. These remnants, white dwarfs, neutron stars, and black holes, were no longer rare oddities born from stellar death. They became the primary inhabitants of galaxies, outnumbering active stars by vast margins. And with their growing prominence, the physics governing the cosmos transitioned from nuclear fusion and radiant energy to the slow, profound, and unforgiving laws of degenerate matter. White dwarfs were the first to dominate. In their early stages, these carbon-oxygen cores radiated heat from the remnants of their former stellar lives. But without fusion to replenish their energy, they cooled steadily, transitioning from bright white to red, then to infrared, and ultimately to darkness. Supported by electron degeneracy pressure, a quantum mechanical effect that resists further compression, white dwarfs remained stable even as they cooled toward absolute zero. Their surfaces crystallized, forming vast lattices of carbon and oxygen, turning these ancient remnants into slowly darkening galactic fossils. Neutron stars, far more compact and exotic, also endured. Their internal structure was governed by neutron degeneracy pressure, a force arising from neutrons compressed into an ultra-dense superfluid. Their surfaces, only a few kilometers across, remained as dense as atomic nuclei. Though their initial magnetic fields and rapid rotation gradually decayed, neutron stars persisted indefinitely, drifting through galaxies as cold, silent monoliths. Over time, some captured passing matter, triggering brief bursts of radiation before returning to quiet isolation. Black holes, by their very nature, came to occupy a special position in this era. Formed from the collapse of the most massive stars and through the merging of stellar remnants, they accumulated mass through gravitational capture. Entire stellar systems, white dwarfs, neutron stars, planets and debris were occasionally swallowed, their mass converted into gravitational inertia. Supermassive black holes, anchoring the centers of galaxies, grew even larger as mergers continued. In a cosmos where luminous activity waned, these titanic structures remained among the last dynamic engines of astrophysical energy. Over trillions of years, the balance of mass within galaxies shifted decisively toward degenerate matter. Normal stars, once the architects of cosmic energy and chemistry, became numerically insignificant. Galactic disks faded, spiral arms dissolved. The remaining glimmers of starlight were dominated by long-lived red dwarfs, embers burning through the final reservoirs of hydrogen. Eventually, even these quiet stars would contract into degenerate cores, joining the growing population of stellar relics. In this era, galaxies took on a ghostly appearance. Their overall luminosity dropped by orders of magnitude. From afar, they resembled faint, diffuse halos rather than the brilliant spirals of earlier epochs. The interstellar medium, deprived of fresh gas, grew cold and inert. Dense molecular clouds no longer formed. Star formation ceased entirely. Yet despite this cosmic stillness, galaxies remained gravitationally coherent. Dark matter continued to anchor their structure, while degenerate remnants orbited silently along well-defined paths. The motions of these remnants created faint gravitational whispers, subtle interactions, long-term orbital decay, and occasional close encounters that sent remnants drifting into intergalactic space. If you could travel through a galaxy in this era, you would enter a realm of deep quiet. Instead of the vibrant, multicolored scenery of nebulae and star clusters, you would pass through vast stretches of cold darkness, dotted with the faintest shimmers of dying remnants. Black dwarfs, completely cooled white dwarfs, passed by like invisible stones. Neutron stars drifted as compact shadows, their once powerful magnetic fields now little more than faint memory. Even black holes, though dominant, would be nearly undetectable unless they interacted with a passing body. The universe had not ended, it had transformed. Radiance gave way to endurance. Brilliant nuclear furnaces gave way to silent quantum-supported relics. And the cosmos entered a phase defined not by creation, but by stability, stillness, and the quiet persistence of matter in its most compact forms. As you absorb this vision, you may feel a deep stillness settling into your awareness, a recognition that even as energy fades, form remains. The universe's evolution is not a collapse into chaos, but a slow glide into equilibrium, guided by the most fundamental laws of quantum physics and gravity. As trillions of years stretched into quadrillions, the universe entered a new epoch, one governed almost entirely by black holes. These gravitational giants, once only a fraction of the cosmic population, gradually became the dominant astrophysical structures. Every star that had the mass to collapse into a neutron star or white dwarf had long since completed its life cycle. Collisions, mergers, and slow gravitational captures accumulated over unthinkable spans of time, feeding black holes and transforming them into the final active engines of an aging cosmos. Most galaxies, now dark and diffuse, still contained supermassive black holes at their centers, monsters millions or billions of times more massive than the Sunday. Even in this quiet era, they exerted immense influence, shaping the orbits of the remaining stellar remnants and gradually consuming anything that wandered too close. Without the vibrant gas flows and bright accretion disks of earlier epochs, these black holes were largely silent, their existence marked only by gravity's invisible pull and the faint ripples of space-time they stirred through their interactions. Smaller, stellar mass black holes drifted through galaxies like solitary shadows. Some traveled alone, others formed in binary systems with white dwarfs or neutron stars, drawing small amounts of matter from their companions in brief flares of radiation. But as the universe cooled and matter thinned, even these interactions became exceedingly rare. Most black holes spent their time isolated, waiting patiently for the occasional collision or passing remnant to deliver a final burst of energy. Gravitational interactions between compact remnants became the primary drivers of dynamical evolution. Over immense timescales, star remnants exchanged energy and momentum through close encounters, an extremely slow process called gravitational relaxation. This caused heavier remnants to sink toward the galactic center, while lighter objects were gradually ejected into intergalactic space. As a result, black holes of all sizes migrated inward, forming dense central clusters around the supermassive black hole at the galaxy's heart. Within these central regions, black holes occasionally merged, sending gravitational waves rippling across space-time. These waves, once detectable only with exquisitely sensitive instruments like LIGO and Virgo, became among the very last energetic signals in the universe, a faint chorus marking the merging of compact objects long after starlight had faded. Each merger produced a black hole slightly larger than before, slowly building a population of massive, stable gravitational wells. Outside these central regions, the universe grew increasingly empty. Galactic disks dissolved, spiral structures vanished. What remained was a faint halo of dark matter, sprinkled with degenerate remnants and black holes. Even planets, once abundant around sun-like and red dwarf stars, were now either frozen beyond detection or swallowed by black holes over trillions of orbits. The few planets that survived drifted in pitch-black space, orbiting cold remnants or rogue black holes wandering through interstellar darkness. As dark energy continued to accelerate cosmic expansion, galaxy clusters became gravitationally isolated islands across an ever-widening void. Eventually, even clusters themselves began to fall apart. Black holes drifted outward or inward depending on their gravitational exchanges, but the large-scale structure of the universe flattened into a sparse landscape of isolated gravitational systems, each containing a handful of black holes and remnants bound only by the local gravity they produced. To an observer which almost certainly could not exist in this distant era, the universe would appear almost perfectly black. There would be no stars, no galactic structures, no glowing nebulae. Only the faint gravitational dance of black holes would break the uniform silence. Time itself would seem to stretch, as fewer and fewer interactions occurred to mark its passage. The universe had entered a meditative state, defined by the endurance of gravity and the silence of compact objects. Yet even black holes are not eternal. Over unimaginable spans of time, they slowly leak energy through Hawking radiation, a quantum mechanical process that causes them to evaporate particle by particle. Stellar mass black holes evaporate over approximately 106710, 1067 years, while supermassive black holes endure far longer, up to 100,100,100 years or more. But eventually, even they fade, releasing their energy into space as a final whisper of radiation before vanishing entirely. As you reflect on this era, you may sense the universe's profound stillness, a cosmos that has transitioned from fiery birth to luminous expansion, from star-filled grandeur to a quiet realm dominated by gravity and quantum decay. This is not destruction but transformation. The universe continues, but in a new form, subtle, patient, and stripped down to its most fundamental structures. As the universe drifted far beyond the age of stars and galaxies, another transformation, subtle, quantum, and profoundly slow, began shaping the final chapters of cosmic evolution. Black holes, long considered the ultimate endpoints of gravitational collapse, appeared eternal to observers living in earlier epochs. But in this distant future, where time stretched into unimaginable magnitudes, even black holes revealed a fragile impermanence. Their dominance would not last forever. Eventually, the quiet erosion of Hawking radiation would become the final active process in a universe otherwise slipping toward absolute stillness. This radiation, predicted by Stephen Hawking in the 1970 seconds, arises from quantum effects at the boundary of a black hole's event horizon. In empty space, particle-antiparticle pairs constantly appear and annihilate each other in fleeting flashes of existence, a restless foam of quantum uncertainty. Near a black hole, however, these pairs can be torn apart. One particle may fall into the black hole while the other escapes, carrying energy with it. To an outside observer, the black hole emits a faint thermal glow, as if slowly evaporating into the vacuum of space. At first, this radiation is negligible. A stellar mass black hole emits so little energy that it would take approximately 10 to the power of 67 years to evaporate completely, a timescale exceeding by trillions of times the current age of the universe. But as black holes lose mass, their temperature rises. They radiate more intensely, accelerating the rate of evaporation. What begins as an unimaginably slow seep eventually becomes a rapid cascade of quantum energy, culminating in a brief and final burst of radiation as the black hole vanishes entirely. For supermassive black holes, the process takes even longer. A black hole with a mass of 1 billion suns might require 10 to the power of 100 years or more to fully evaporate a number so large it challenges human intuition. Yet even these cosmic leviathans eventually succumb to Hawking radiation. In the final moments of their existence, they release a concentrated burst of high-energy particles, briefly illuminating the silent void with a last faint echo of their ancient gravitational might. As black holes shrink, the universe grows emptier. Matter once locked behind event horizons is slowly returned to space as radiation. But this energy disperses into an environment that has become exceedingly cold. The temperature of the cosmic background has fallen far below a trillionth of a degree above absolute zero. Photons, neutrinos, and the faint particles from evaporating black holes drift across a cosmos where interactions are nearly non-existent. Time itself begins to lose meaning as the markers of cosmic evolution fade. By the time the last black hole evaporates, the universe has entered a state known as the Dark Era, an epoch where no stars, no galaxies, and no compact remnants remain. Only elementary particles, far-flung photons, and the faint echo of quantum fluctuations populate the fabric of space-time. Gravity still exists, but with no large structures left to shape, it exerts little influence. The expansion of the universe continues, driven by dark energy, stretching space until all remaining particles drift into near-perfect isolation. If you could observe this era, a perspective no consciousness is likely to survive to acquire, you would witness a universe where black holes glow softly in their final stages, each one a solitary beacon of quantum fire amid an ocean of expanding darkness. Their evaporation is the universe's last display of coherent energy release, the final performance of physics as it once operated on macroscopic scales. After this, the cosmos drifts toward an even quieter existence. And yet, within this serene emptiness, there remains a sense of completion. Black holes, once symbols of cosmic finality, return their energy to the universe. The cosmos, having formed complexity from simplicity and then dissolved complexity back into simplicity, enters a kind of equilibrium, a smooth, diffuse state where entropy reaches its maximum and structure becomes memory. As you let this vision settle in your awareness, you might sense the profound gentleness in the universe's distant fate. Even its most powerful entities, black holes, do not end in violence but in soft release. The cosmos, in its final breath, becomes quiet light dissolving into infinite stillness. With the last black holes evaporated and the final bursts of Hawking radiation faded into the vastness, the universe entered its most silent and minimalistic epoch, the Dark Era. This was the cosmic horizon beyond which all astrophysical structure had dissolved. No stars, no galaxies, no remnants, no light. Only a thin, sparse fog of elementary particles drifting through an ever-expanding space-time, separated by unimaginable distances. The universe, once a brilliant arena of nuclear fire and gravitational sculpture, now resembled a vast cold ocean where ripples of energy and matter drifted without ever encountering one another. Entropy, the measure of disorder, had climbed to its maximum value. Every process that could smooth differences in temperature had long since done so. Every gradient that once drove motion or chemistry had flattened. Even the faint glow of particles released from evaporating black holes had redshifted into wavelengths so long that they were essentially indistinguishable from nothingness. The temperature of space approached absolute zero, only infinitesimally above it, due to the quantum jitter inherent in the vacuum itself. In this era, particles existed in almost perfect isolation. A lone positron might drift for 1 trillion years before passing within light years of an electron, and even then, cosmic expansion ensured that interactions were exceedingly unlikely. Protons, if they are unstable, would eventually decay into lighter particles, positrons, neutrinos, and photons. If protons are stable, a question still open in modern physics, they would drift forever. Either path leads to a universe devoid of meaningful structure. Only the vacuum remained, stretching endlessly. Even quantum mechanics took on a different flavor in this lonely cosmos. Vacuum fluctuations still produced ephemeral particle-antiparticle pairs, but without gravity wells or electromagnetic fields to shape them, these fluctuations emerged and vanished like faint ripples on a perfectly calm surface. No galaxies to distort them, no stars to illuminate them, no observers to measure them. The universe became a quiet quantum sea, a smooth field of nearly uniform emptiness. Space-time itself, driven by dark energy, expanded at an accelerating rate. The metric stretched so rapidly that particles once separated by inches were soon separated by kilometers, then by light years, then by distances so vast that no meaningful physical relationship could remain between them. The universe had become a patchwork of isolated coordinates, regions so far apart that even the concept of distance lost its relevance, since no signal could ever traverse the expanding gulf. If consciousness could drift through this era, it would experience an endless horizon of darkness, not hostile but profoundly empty. There would be no sense of direction, no reference point, no motion, except the inherent expansion of space itself. Time, though still existing, would feel meaningless because nothing changed. No cycles, no interactions, no events. A moment 1 trillion years long would feel identical to a moment 1 quadrillion years long. The universe had entered a perfect stillness. Yet to say the universe died would be a misunderstanding. This was not destruction, it was a natural settling. A return to equilibrium after an incomprehensibly long journey from the fiery density of the Big Bang to the silent dispersion of the far future. The cosmos had expanded, cooled, structured, evolved, collapsed, scattered, and finally smoothed itself into a state where no further transformation was likely. It was the ultimate expression of thermodynamics. Energy spread across such vastness that no organized phenomena could arise again. And in this emptiness, there is a strange form of peace. A universe that once burned with stars has exhaled all its brilliance. A cosmos that once roared with supernovae and collided galaxies has softened into a faint whisper of particles. It is the final resting state of everything that ever was, a serene stillness at the end of an impossibly vast timeline. As you settle into this vision, you may feel a profound sense of scale. The universe's journey mirrors the arc of existence itself: birth from chaos, growth into complexity, slow decline, and eventual stillness. And in that stillness, there is a quiet beauty, an echo of every star, every world, every moment that came before. In the vast stillness of the dark era, where particles drifted in solitary silence and space-time stretched beyond all intuitive scale, the universe approached a state that resembled a cosmic exhale, long, slow, and final. But even in this near-perfect equilibrium, the universe carried with it a quiet echo of everything it had once been. An imprint of the Big Bang remained woven into the very fabric of space-time, a faint memory stretching across eternity. It was not light, nor sound, nor any familiar form of energy, but a subtle curvature, a lingering geometric whisper that the universe had once been young, dense, and bright. This echo existed not as a physical phenomenon that could be measured or observed in this distant epoch, but as a structural truth of space-time itself. The expansion that began in the earliest fraction of a second continued, diffuse and unstoppable. The cosmic microwave background, the original afterglow of creation, had long since redshifted into wavelengths larger than galaxies. Yet, the pattern of that radiation, embedded in the structure of space-time, still traced the earliest quantum fluctuations that seeded galaxies, stars, and eventually life. Even after the last black hole evaporated, even after protons decayed, that imprint endured like a faint tide mark on the shores of existence. In this final era, the universe may appear empty, but it is not meaningless. Every particle that drifts across the cold vacuum carries within it a lineage, forged in the furnace of the Big Bang, shaped by gravity into stars, scattered through supernovae, condensed into planets, cycled through chemistry, and reabsorbed into the cosmic weave through collapse and radiation. The universe is quiet now, but its silence holds the full story of everything that ever unfolded. In a sense, the entire cosmos has become the memory of its own creation. Some theories suggest even deeper echoes. Quantum cosmology hints that the universe, once stretched into near-perfect smoothness, may reach a state where fluctuations again become relevant. Perhaps the vacuum, unstable in subtle ways, could tunnel into a lower energy state, triggering a new burst of inflation, a new expansion, a new cosmos born from the ashes of the old. This idea is speculative, unknowable, and far beyond the reach of observation. And yet, in the profound quiet of this final epoch, such possibilities feel almost poetic, that the universe might one day breathe again, igniting a new cycle of time and structure. But even if no new universe arises, the one that exists now has already completed a journey of staggering beauty. From the blazing density of the Big Bang to the formation of galaxies, to the birth of stars and worlds, to the rise of chemistry, biology, consciousness, and finally, to the serene dissolution of structure, every phase unfolded according to the same fundamental laws. The universe did not rush, it did not falter. It simply evolved, step by step, from pure energy to infinite complexity and gently back towards simplicity. If you could float within this final moment, not as a being bound by biology, but as pure awareness, you would experience an indescribable calm. No stars to overwhelm the senses, no gravity wells to distort motion, no radiation to interrupt silence, just the smooth, soft geometry of space-time stretching endlessly in every direction, a canvas washed clean, yet holding the ghost of every galaxy that once adorned it. And in that vast stillness, you might sense something profound, that the universe was never truly about stars or planets, or even life. It was about the unfolding of possibility, about the quiet laws that allowed something to arise from nothing, structure from chaos, meaning from silence. The Big Bang was not merely an event in the past. It was the opening note in a cosmic symphony whose final chords now fade gently into the dark, a symphony that shaped every atom, every breath, every thought you have ever known. And now, in the quiet end of time, the universe returns to calm, a calm that holds within it the full memory of its beginning. This is the echo of the Big Bang. This is the silence after creation. This is the universe at rest.